Okay, so today we're going to look at the Fourier transform. Okay, so we've just seen the Z transform, which was a way of going from the discrete world to something relates more to frequency. Now we're going to look at the Fourier transform, and we're only going to look at it in the continuous domain. Okay, so we're going to look at the Fourier transform in the discrete domain after this lecture, but right now we're just going to be looking at the extension of the Fourier transform in the 2D world. Okay, so remember the Fourier transform. So the idea is like you have a signal and you want it to represent it as the in terms of sinusoids of different amplitude and frequency. Okay. Now, in 1D, you only had two parameters really for the sinusoid. You had the frequency and the amplitude, right? And but in 2D, obviously, you actually have two frequencies. So you have the frequency in the x and y on the two axes. Okay, so omega 1 and omega 2. So phi here is your phase of your sine on your sinusoid, and A is your amplitude. So when you look at the profile of that in 2D, you get so that would be a picture representing this as a the picture. So you have this kind of waves pattern. So this is a 3D representation of that. So a few notes on that. So okay, so you still have your wave. This time it has a direction. Okay, and so these two frequencies in x and y. At the end of the day, what you get out of that is still you only have like a sine wave, but directed in space. Okay, so you still have kind of a 1D sine wave, but except you have like a real wave on the sea, you have a front. Okay. Some point on the notation here, and something we didn't really have an explicit definition of it. When you look at omega, for instance, it's expressed in a radian per pixel, and you'll see me saying a lot, or in the handouts, we use the word pel. Okay, so for picture elements, so pixel is a picture element, and so the other way of saying it, it's pel. So PEL is a shorter version of pixel. Okay, so just be aware of that small point here. Right, so that's the analysis here. We can try to express signals in terms of this and these waves, and let's see. So you have detailed notations here, but if you look at the handout, basically, let's think backwards. Okay, so that's the exact expression we have. So with your two angular frequencies, omega 1 and omega 2. And what we say that actually you can represent these two as you can factor in, you can do a change of coordinate if you want. And you say that omega 1 can be defined as a base frequency omega 0 times a cosine theta, and omega 2 as a base frequency omega 0 times sine theta. And so when we say that this expression could be just replaced with this expression here. And all I've done here is kind of change the naming of it. So instead of having omega 1 and omega 2, now have omega 0 cos theta and omega 0 sine theta. Think of it as polar coordinates. Okay, so you had in Cartesian coordinates you had omega 1 and omega 2, and now in polar coordinates you have something is called omega 0 and the angle where it goes to. So these two notations are, you can go back and forth. You can go from omega 1, omega 2 to omega 0 theta and back. And if you write it this way, then it becomes clear what's going on. Okay, so you really have this direction theta, which is the direction of your wave, and you have a base frequency, which is this omega 0. All right, just a small point to say, these two terms, omega-1x, omega-2y, they still yield to just one wave, but just with a direction on that wave. Right, so here comes the nasty Fourier equations. There is nothing really different from what you've seen in 3C1. So it's really just the same, except with, instead of having just one integral, okay, so this is what you've seen in 1D. So you had the transform is integral of x times this exponential of minus j omega t. So here what we have, because we have two frequencies, okay, so you have the frequency in x and in y, and therefore you have two integrals going from y from minus infinity to plus infinity, and minus infinity plus infinity for x as well. So that's kind of what we get. There's no really, it's not much different from what you have in 1D. It's really the same, except you integrate over the entire domain, and the domain is 2D. The inverse Fourier transform is as follows. Now remember, there's different ways of defining where you put this constant number. Okay, so either it goes into the Fourier transform definition, or in the inverse, or a mix of both. But just basically remember, when you do the inverse Fourier transform in our definition here, you have this constant here, 1 over 4 pi square, that you need to take into account. All right, so nothing new, scary equations, but really nothing new for you. As you had for 1D, still true here. So if you have a convolution in the continuous domain, when you look at the frequency domain, then you have a multiplication. All right? That's kind of the whole point of that is to have a transformation that allows you to do multiplication in the deal with a convolution in a nice way in the frequency domain. Side note: so the Parseval theorem is the same. So basically the energy of your signal in the continuous domain is the same as the energy of your all your frequency components. All right. So a number of points actually turns out to be quite useful for us, properties that will be useful for us, okay, in the future. So the first point is the fact that the 2D Fourier transform is separable. And by that, we mean that, okay, so when you look at it, you say, well, now we have to integrate over the entire area. Therefore, you could think that doing the Fourier transform in 2D is way more complex than in 1D. Okay, maybe the computational complexity that when we'll be working in the 2D domain would be way heavier. Okay, and it turns out it's not true. Okay, so that's one of the wonderful things about the Fourier transform is that there is a neat trick here that so if you reorganize your computation and try to put here, so you just split. So you have this term here that has these omega-1x and omega-2y, and because that's in the exponential, we already have the product of two exponentials, okay? And so now I can actually separate out all the terms that depends on x as one integral in x, and then have the terms in y outside of that. And so there's nothing really fancy here, but the important point here is that this expression, what it is just the Fourier transform along the x-axis. All right, so said differently, okay, so if you want to do the Fourier transform in 2D, you only need to do how to do it in 1D. And the way you do that, so you take your picture, you take every single rows if you want, and you do the Fourier transform of all these rows in 1D. Okay, so you extract all the rows, and a bit the way you've done that with histograms, for instance, the problem you had with MATLAB. So here is like you say, well, I know how to do it in 1D, so I'm going to take all the rows I have in my picture, I'm going to apply the 1D Fourier transform on these rows. And it gives you back a new picture. It's a picture of complex numbers, so not much you can see. But every single row now is the Fourier transform of that row you had in picture. And so you have that, and that's these intermediate results that I've highlighted. So that's a Fourier transform along the x direction. And then you take that result, that complex image, and you compute the Fourier transform along the columns this time. So you looked at every single column of that result. And now you have a 1D vector of complex numbers, and you can compute the 1D Fourier transform on that column, and you apply it, and that's what you do it now. And you get now the Fourier transform. The result of that second Fourier transform is a 2D Fourier transform. So it's quite interesting. So you can break down and say, what the cost of doing Fourier transform? Well, it's just the cost of applying Fourier transform in 1D twice. Okay, so you apply it first to get along the x-axis, and then apply on that intermediate result, you apply the Fourier transform along the y-axis, and you get your 2D Fourier transform. Works in ND as well, okay? So if you work in 3 dimensions, if you work with a cube, you can do easily the Fourier transform in 3D by just doing first in x, y, and then in z, okay? So looking at the equations, you'll be like, okay, all that is quite nasty, have some joint stuff, that really depends on where it is, and especially, and you might fear that doing something in 2D is way more complicated, but actually it's not, okay? So doing an ND Fourier transform is only n times the cost of a 1D Fourier transform, all right? And that's kind of very powerful results that makes a Fourier transform very attractive, okay? Right, so that's the first point, okay? The fact that you can easily compute the 2D Fourier transform by just doing the Fourier transform sequentially in every single axis of your space. The second result that will be useful for us just later on is the fact that it's kind of obvious from previous definition properties we had, but if your signal is a convolution itself of 2 signals, so say in the lab we've seen the Gaussian blur, and we say that the Gaussian blur in 2D could be expressed as as actually 2 convolutions back to back of blur in the x and blur in the y direction, right? So basically, what we say that the blur mask can be obtained as a convolution of a blur max in x times convoluted by a blur max in y. But if you have that, then it means that the Fourier transform of that 2D mask is actually just the product of the Fourier transforms taken separately on the 2 masks. That comes down to the fact that the convolutions become multiplication later on. The last point is that for real signals, you have some symmetry going on, and this is the exact expression of that symmetry. So if you have a particular frequency in x and y, then you can find that the frequency in minus x and minus y is the complex conjugate, of that number. That means like when you're going to look at the Fourier transform of the image, you're going to have some symmetry, very strong symmetry around the center. Now remember, Fourier transform, okay, is bizarre stuff, but you have negative frequencies, okay? Just because you can plug in negative numbers in the equation and it still works. So you have negative frequencies. And so basically what we say here is like negative frequencies are related to positive frequencies, okay? So they're kind of the same stuff, really. Right, so let's look at the basic example, and because we're working with signals, at some point we're going to use this kind of pulse function, okay? And so in 1D, the pulse was just 0 everywhere, and then 1 for a particular length of time, and then comes back to 0. But here we're working 2D, so really what you have is some kind of rectangle that is elevated and 0 everywhere. And that's the kind of function you will use, for instance, for sampling your signal or doing this kind of stuff. So let's see, so it's a particularly important signal to study. And so we're just going to write down do the exercise of computing the Fourier transform for that. Now, okay, so this is the definition of our, I just call that rectangle of AY and ABX, okay? So, if I say that my function, this rectangle function, the first thing I'm going to say that it turns out that it's, because it's symmetric, okay, in X and Y, separable, sorry, in X and Y, you can actually say that it's a convolution of just this 1D signal in Y and 1D signal in X. Right? So basically what's going on in X and Y is kind of independent. Right? So because of that, I can separate that and just say, well, it's a convolution of these two signals. Coming back to your blur function, that kind of makes sense. Right? So the blur function was the convolution of itself taken in the X and Y direction. And here we do the same for the rectangle. So we know what the 1D transform for a pulse is, and that's something you would have done. Basically, it's a sinc function, right? And I've done here the detail of that to kind of remind you how it works out. So you do the Fourier transform over the entire domain. So this is in 1D. And basically, your signal is 1 between minus b over 2 and b over 2, and 0 elsewhere. Okay? So that's what your signal is, the basic rectangle function. So therefore, the Fourier transform is the integral between minus b over 2 and b over 2 over the exponential. And you take the integral part of that, and you get a difference between these two guys, and you have to divide by 1 over j omega 1. And that, when you reshuffle that, is basically a sine function divided by omega 1. And so that's called sinc. Right? I invite you to redo these computations. I know they're in the slides. I'm kind of going fast here. I invite you as an exercise to redo all that aspects, okay, to check back why this is and why the Fourier transform of the rectangle function would be this sinc function. I mean, this is a useful exercise to do again. Anyway, because we know that the rectangle becomes a sinc function, and because we know that this is a convolution, and the convolutions in the Fourier domain becomes a multiplication, the final Fourier transform that we're looking for is basically this entire expression, which is just the two sinc functions multiply, so the sinc function in the x and y, basically. So let's see what it looks like. So on the left, you have the picture domain, and on the right, you have the frequency domain. So that's your definition of the function, and you can see here a profile of that, what it looks like. So if you display that as a picture of the frequencies, or at least the magnitude of the frequency, what you get is this kind of ringing phenomenon. Okay, so mid gray here would be 0, and dark means it's negative, and white means it's positive. Okay, so and this is what it looks like here. All right, so so remember, okay, so this is kind of something you've seen in 1D. Here, the pulse has a massive discontinuity. Okay, so when you go from here to here, there's a sharp discontinuity, and therefore, what you can expect in the Fourier domain, like in the frequency domain, is a big mess. Okay, so you're going to have frequencies spreading at infinity. Okay, so you're going to have frequencies at the highest number you can think of. Right, so when you have something sharp, a sharp feature here, that will translate into high frequency here, very high frequency, in fact. All right, so It's kind of like there's, it's kind of the trade-off you have working with frequencies. Does it make sense? Kind of this, you know, all that is just extension of what you've seen in 1D to 2D. Right, some kind of interesting points about what's going on, properties of the Fourier transform. So, and this relates to geometrical transformation of your picture. So the first one, so we start from a picture domain. So remember here we're working in continuous domain, okay, continuous definition. And so this is your image and this is the Fourier transform. So if you translate your picture, okay, so if you take your picture and just translate it by dx and dy, okay, so you have an offset. You just move the picture as a translation. What happens to your Fourier transform is interesting. So basically the Fourier transform stays unchanged, but you apply this, this change of phase, okay? So you apply it, you multiply, it's a pointwise multiplication of all the elements in, or all your Fourier transform points by this function, this exponential of minus j omega 1 dx, blah, blah. If you take the norm of that, okay, the norm of this factor here is 1. All right, it's just exponential. So not changing the amplitude of the frequency, okay, so the amplitude of, if you look at the power spectrum, which only looks at the amplitudes of your frequency, stays the same. So if you translate the picture, that doesn't change the power spectrum, but I would change the phase of your complex numbers, okay? So the phase will be changed. So basically, when you'll be studying the Fourier, you know, like practically, when you'll be looking at frequency maps or doing Fourier transforms, when you visualize what's going on, most likely you'll only be looking at the phase, and so if you do a translation of your picture, you won't see any difference in the results of your Fourier analysis. If you do something a bit more complex, okay, so if you have a transformation, so here x is a coordinate xy, and you have some kind of matrix representation of how you do your transformation. This is the generic transformation you have, okay? Now, you don't have to know about that by heart, but I just wanted to point out two special types of transformation that are kind of useful. So the one is a zoom, okay? So zooming basically means you transform the x and y coordinates into something like ax and ay, okay? So if you divide x and y by 2, what happens is like you're going to basically zoom out or zoom in, one of the two. You're going to zoom out or zoom in the picture, right? So that's a zoom, okay? So you just multiply x and y by some number, and then you get a picture which is basically a zoom version of that picture. So you see, so you can define the matrix A corresponding to zoom, and when you look at this part here, so you have this constant factor here that would have an impact. But if you look interestingly at this transformation, which tells you what kind of transformation you have in the Fourier domain, then you realize that actually it is the same. It's a zoom, but of inverse, okay? So what it means, like if you zoom in a picture, then you zoom out in the frequency domain. Or if you zoom out on the picture, then you zoom in the frequency domain. Another way of thinking about that is if you zoom out on the picture, then the frequency that requires low frequency, so low frequency would be, say, a flat region, okay? So there's not much going on. If you zoom out, then this flat region might not be that flat anymore, okay? So what looks like a plane from the ground, from high up in the sky, looks like maybe a very rugged terrain, okay? So therefore, when you zoom out, the frequencies will be much higher, okay? So the frequency looks like the frequencies are much higher, okay? So when you zoom out, the frequencies looks a bit higher. And when you zoom in, then everything looks a bit smoother. So this is what's happening. So when you zoom in, it's like the same effect as zooming out on the frequencies. The second interesting transformation is the rotation. So you have here a rotation matrix to rotate your picture. And when you do the transformation, when you look, what happens is that in the Fourier domain, it's a rotation as well. Okay, so if you rotate your picture, the Fourier analysis will be exactly a rotation. You won't see a difference. Okay. All right. So two interesting points about geometric transformation. So let's see what it looks like in real life. Okay. So obviously these are not continuous pictures. So this is just a discrete version of that. But it's still valid. Okay. So on the top. This is the linear picture, so that's a standard test image. And this is what the Fourier spectrum looks like. The point here, so dark, okay, so looking at the frequency here, the amplitude, sorry. So dark means closer to 0, and bright means high value of amplitude. And the point here in the middle, the one that's very bright, is obviously the frequency 0, 0 on the x and y axis. Okay, so frequency 0 means it's what the constant number is. That's the average value of the entire picture. Does it make sense? So that's the frequency 0. So when you're close to here, you're looking at frequencies of very low frequency, so very slow changes in the picture, like if you want kind of a blurred version of your picture. If you want. When you're further out, what you're looking at is frequency that impact pixel differences, like almost like noise level. Very small frequencies, very high frequencies over the picture. So there will be changes that happen from pixel to pixel in a very, very fast way. So obviously, what you get natural images, you have this, so the spectrum is spread over the entire space, okay? So you have, it's a bit of a mess. But interestingly, here you had all these structures happening and all these kind of features. But when you are in the Fourier domain, these two pictures are vastly different. But in the Fourier domain, they kind of look like the same, all right? And what's happened here is like all the values, or all the energy, if you want, it's called energy, seems to have been compacted in the center, in the low frequency parts. Okay, you seem to have kind of a similar shape regardless of the type of picture you have on the inputs. Okay, so I mean, if you just look at the Fourier transform, it's very hard for you to tell me which one is which. Okay, and they kind of both look like the same, where these two pictures are vastly different. And that's kind of the idea behind compression. Okay, the idea of like using transform for compression is exactly that. So when you do Fourier transform, you end up in a space where there is something that is common to all these pictures. Okay, there is some kind of a higher level of statistics. You can say most likely the 0, 0 frequency is higher than the very high frequencies. Okay, so you kind of have some prior knowledge of what to expect from the picture. Okay, and that's something that's valid for most pictures you see. And that information you have about what to expect in the frequency domain is something very useful. That's something you'll be able to take care of to take advantage of in the compression. And that's something we can see later on. But just wanted to point that to you. Okay, so we transform, and now we get to a domain where things kind of look similar, and that's interesting. Maybe you can see some stuff. Okay, so here, okay, you can see there's some kind of a vertical feature in the Fourier transform. Can you tell me why you see that vertical structure here? Can you have a guess of why the there's more. There seems to be kind of higher frequencies in that axis. All right, so it corresponds to something in that picture, okay? And that picture, when you look at it, there's quite a high vertical contrast going from here, from the trees to the beach, okay? So all of a sudden you can see like there's almost like a, think of your rectangular function. There seems to be a step going on from the bottom to the top path, okay? I'm just talking roughly here. So that means that you can expect in the frequency domain to see quite a lot of these frequencies trying to model that here. Okay, so remember your sinc function. The sinc function gets spread out quite far in your domain. So that's what's happening here. So all this strong edge, which is kind of almost horizontal, means that you have a massive vertical discontinuity, and means that this vertical discontinuity will have an impact on the vertical frequencies. All right, so that's kind of why you see this spread. Same here. Okay, you have this horizontal high contrast between black and bright, and a bit here. So it's quite a lot of things going on in this diagonal direction. And you can see that here, that spread coming along here. All right? It's kind of subtle effects, but you can start to pick up these kind of features in that world. So anyway, so that was done on the entire picture. Usually we'll see doing that exercise on the entire picture is not very useful because it's too much of a mess. Okay, so you here could maybe identify big things happening in the picture. So most likely, most of the transform, if you look at JPEG, that is closely related to the Fourier transform, they will split your pictures into blocks. So here, split that into blocks of 32 by 32 blocks. And I computed the Fourier transform. Now, the blocks are finite in dimension, and therefore it creates all sorts of things. So you need to use windowing, and something we'll see a bit more in detail. But you've seen that in 1D as well. When you look at chunks of data, you need to have kind of make it more periodic. So one way of doing that is to have windowing. But anyway, this is a detail. So on the left, you have the original blocks. On the right, you have the Fourier transforms on these blocks. And it becomes very clear what's going on. Okay, so if you have a block like this, which is not much going on, like low frequency, then you can see here that all the energy, all the high, the amplitudes of your spectrum is really concentrated on the low frequency in the DC component, so the 0,0 frequency part. If you have a strong edge, so you take this one here, okay, or even this one, okay. So this one you have an edge going from this diagonal. You can see in this block clearly that you have this diagonal represented as well, okay. So then it becomes kind of more clear what's going on, okay. But interestingly, really, when you see these guys, you can see like there's most of the signals here are either concentrated in 0 or kind of spread along these lines. But there seems to be kind of a clear pattern on how things behave, and the range of possibilities here seems to be a bit lower than the range of possibilities here. Okay, so the key element here is like working in the Fourier domain seems to tell us that there's when you look here, like, it looks more noisy, okay? And this noise actually is something we could model and could say, right, this is flat, or we just replace the noise with something else. And when we do compression, that's what we do. We say, all the noisy part here is not important, we just remove it, okay? And we'll be able to simplify these pictures in the frequency domain. And then after we apply this simplification, we'll be able to come back into the picture domain and still get something interesting. We just remove the unnecessary frequencies and stuff like that. Right, so that's kind of what I said here. Let's see. You know what, we're going to stop here because the next lecture it's quite more heavy. It's about sampling, okay? So maybe you want to, so make sure I have the slides up, but maybe you want to check back the sampling stuff you've seen in last year's lecture. It's all about how the effect of sampling on the frequency domain, okay? And aliasing and so on.